And for audience online, can you see the my screen sharing?
Mm-hmm.
Okay.
Yeah. Yeah.
Okay. Cool. I also want to check audience at the back end. Can you hear my voice clearly? Okay, cool. Hello everyone. So my name is Changyu Mu, and right now I'm a CSD PhD working with Yilin Shi. And today I'm sharing our recent work about building up public encryption from this problem called MinRank. And this is a joint work with Rohi from NUS and Prashant, who is my bachelor supervisor, also from NUS. So I want to make sure that everyone can learn from this talk. So in case that any part or any notation that you find confusing, just let me know and I'll explain to you. So we're working on the general secure communication setting where you want to send a message to a friend through an untrusted channel. So you want to send a message M, which let's say is either 0, 1, to your friend. And this channel is untrusted in the sense that there might exist some adversary who want to learn your message passively. And what we want is to ensure the secure communication despite the existence of such adversary. And what we're working on is this specific setting of a public encryption, where there exists a pair of different key, a public key, which is given by everyone, including the adversary. And the secret key, which is kept private by the recipient. And so if you are the sender, you want to send a message to your friend on the right-hand side, you'll use a public key and encrypt the message, send the what we call the ciphertext, which is the output of the encryption to your friend. And we want the public encryption to work in the following sense. Firstly, we want to ensure that your friend, this recipient on the right-hand side, who has the secret key, can decrypt and get the same message that you sent. We call this correctness property. And secondly, we also want this public encryption to be secure. Intuitively, we don't want the adversary to learn about your message, the message that you sent. But formally, we can define the following, that if you're given a public key, which adversary also has, you're unable to distinguish the encryption of 0 from encryption 1. This way you cannot, because you cannot distinguish these two, you cannot learn the plain text or the message from the ciphertext. So we want the public encryption that has these two properties. This public encryption, or in short PKE, turns out to be a central notion in cryptography. It's actually extremely useful in our real life. For example, when you're surfing on the internet, you may see this header HTTPS, or when you're sending email to your friend. In all these scenarios, the public encryption helps building up the secure communication between you and the other side. And the PKE turns out to be also a fundamental info for some cryptocurrency. So PKE is good. We want to build up PKE. The question is whether we can build up public encryption, PKE. The answer is yes. Since around 70s, there are already multiple beautiful protocols build up PKE from some number theoretic problem. So in cryptography, we want to have provable security in the sense that, as we define, we don't want the adversary to learn this message. So this task of learning the message must be some hard task. And the way we make this public encryption provably secure is that we can reduce the security to some problem, computational problem, that are widely believed to be extremely hard. This way, if the adversary cannot solve this computational problem, then cannot break the security. And back to 70s, there are a few very good protocol of public encryption built upon some hard number theoretic problem. These protocols were optimized and they were made practical and implemented. This are basically what we're using today. However, it turns out that these number theoretic problems are not secure against some quantum algorithms, such as Shon's algorithm. The Shon's algorithm can break like factoring problem, discrete law problem, like inherently you will break this number theoretic problem in polynomial time. Even so far, nobody has ever implemented a quantum computer that can indeed run the Shon's algorithm. But the theory is there. And our goal is to build up a public encryption that is secure. Even one day there is a quantum computer that can run Shon's algorithm. And this leads to this topic of post-quantum cryptography or post-quantum PKE. So the goal is to build up PKE that is secure even if you have post-quantum computer. And what people in post-quantum cryptography community are excited about is this NIST post-quantum proposal. So NIST is a United States institute that is in charge of the security protocol. And they have a proposal asking for a proposal of a PKE in around 2016. And by far, there is one candidate proposal was selected in the standard. And that candidate is based on a candle problem we call lattice problem. And a little bit history, like during this selection of the proposal, there were 3 algorithms, like another 4 algorithms actually entered the last round. But turns out one of them, this one, based on isogenics, this is another type of problem, was broken afterward in around 2022. So somehow like nobody can assure that this problem will never be broken. Nobody can say that. What we have right now is that after so many years of study, there's no such algorithm that can solve this problem even near efficiently. And like for both quantum algorithm and the classical algorithm. So it turns out that the development of a post-quantum PKE is like a game of cat and rat. Like on the one hand, the cryptographer, when we see like there are classes of problems that are believed to be extremely hard against both the classical and quantum algorithm. So we start to use this problem to build up cryptographic schemes. And sometimes, like because this design algorithm is tricky, cryptographers may use some additional assumption in order to make the encryption decryption work. On the other side, there's on the left side, there's an intensive study of cryptanalysis. What their goal is on the opposite. They just want to break all these problems or break these constructions. So in fact, like nobody can assure that this one assumption will not be broken one day. But what we can do is to diversify the post-quantum hardness assumption foundation, in the sense that if, let's say, we have PKE, we can have PKE from multiple classes of a problem. Even if, like what we saw, one problem is broken, we still have hope for secure PKE in the future. The development of PKEs, usually it's a tricky task. The reason is that somehow we need to build our PKE based on some hard problem. And if the problem is extremely hard, we don't even have good understanding of the structure of the problem. We also don't know how to design encryption and decryption from this problem. So that is to say, like, there are many problems that are extremely hard. Maybe they are extremely hard, but we don't know how to construct PKE from them. This is why, like, so far there are only a handful of problems that leads to PKE. And our focus today, this MinRank problem, is one of this kind. Like, it's believed to be extremely hard for a long time, but the people don't know how to build up PKE from it. So our main contribution is to do this. So to move ahead, like, let me give you a bit introduction of what this MinRank problem is. So MinRank problem is a problem that's related to the notion of a matrix rank. If you're not very familiar with this, matrix rank is just a notion that somehow quantify the capacity of this matrix, or like the number of linearly independent rows in this matrix. Let me give you some intuition in case it's unfamiliar to you. Like, looking at these two matrices, which one do you think has higher rank? Like, yeah, maybe give it a try. I think most people look on the right hand side, if I'm not wrong. So it's like, I mean, at least like this looks more complex. It's obvious. And intuitively, and the rank matrix rank in field 2 can be defined as following. Can be defined as the minimum integer r. The rank for matrix E. This E, let's say, it's of dimension n by n. And the rank of E can be defined as the minimum R, such that this E can be decomposed as the product of two R by n rectangular matrix. So let's say if R is very small, somehow you can compress this big matrix by decomposing into two small matrices. And you can save space if you really want to save the matrix. And you can also see, like, if this matrix is a uniformly random matrix, and we know that we cannot compress it, so that means the rank must be high. So the MinRank problem is defined, is related to this matrix, right? And it's in particular defined in the following way. It's composed of two parts. And let's first look at the first part, which is A. A is a tensor, this tensor. It's an n by n by k tensor. The other way to think about this is that, think about like a k slices of a paper from A1 up to AK. There are k slices of paper. And they are uniformly random. Then the second part, you are to sample the second part, you do the following. You firstly sample a random Boolean vector S from S1 to Sk. And then you use this S to select a subset of A. In the sense that if, let's say, S1 equals 0, you just leave A there, A1 there. If S2 equals to 1, you take the second slice A2 out. If S3 equals to 1, you take the third slice A3 out, and so on. So select a subset of A, and then you sum them up over F2, this field. The other way to put this is like you just define linear combination of A using S. And you get this part we call AS. And then in the end, you will add a random low rank matrix E. Let's say it's a random matrix subject to the rank is less or equal to R. So in short, the MinRank instance is composed of two parts. The first part is a tensor A. And the second part is just a matrix, n by n matrix, AS plus E. Okay. And the MinRank problem is to ask you, distinguish a MinRank instance from a uniformly random tensor of the same dimension. So you can think it as like if you're given either the left-hand side AP, or you're given the right-hand side, which is just a uniform random. And you ask to tell which one is which. It looks somehow, this problem turns out to be a hard problem. Let me tell you like something we know about this problem. Firstly, sure.
S is not given, right?
S is not given. Yes. This is an extremely good question. Yes. So P is composed, so it's computed as AS plus E. And the problem is ask you to distinguish AP from A and uniform random. So you're only given either AP or a uniform random tensor.
S is fixed or S is random?
S is random.
The distribution of sum of AI SI is still this distribution of a random matrix.
It's not. It depends on the parameter choice. Let's say if a K is equal to N, then like a n by n matrix contains n squared number of bits. And given A, in order to compute P, it takes you this S, which is just n bit. And this low rank matrix E takes you around n times R. If let's say R is extremely small, let's say R just equals to 2, then it will take you like around 2n bit. So given A to compute P, it takes you around n times R number of bit. But here on the right hand side, this uniform random n by n matrix takes n squared uniform random bit. So that's the difference. Good question. Yeah, this is actually a very important question.
Can I ask,
yes.
What are the parameters like R compared to K and N? Like how should I think about these parameters?
Yeah, that's an extremely good question. So for the rest of the talk, let's say we think K to be equals to just N. Yeah, just K just equals to N. So it's like a cube. The A is a cube. And the R, let's think it as a square root. Yeah, square root.
Okay.
Yes.
Well, this question is like for this paper, like you're looking over F2. So
yes,
I think like are there any so like what are the changes of the regimes when like go to F2 like for them?
Yeah, that's a very good question. So here for simplicity, I presented over F2. That's like easy for everyone to understand. And furthermore, our construction will just naturally extend it to FQ.
So any like circular regime you mentioned there, like extended to F2?
That's also a good question. Let's also recall that because we built up the PKE based on the hardness of the problem. So what I think Li Ran asked was that whether this problem is hard over FQ. Yeah, and so I think it's a very good question. To answer this, I do believe that we need to extend the study on this. Yeah. What I'm claiming is that our our construction will work for both cases. Yeah, so hopefully it's clear right now what the MinRank instance looks like. And I'll also tell you a little bit more about what like already know about it. Like firstly, it's an NP hard problem since it's an introduction. It's a known. And we can also try to examine like how hard it is by using the most brute force way. Like we can think of a run brute force attack to understand how hard it is. Recall that the MinRank instance is composed of A and AS plus E. If you know this secret S, then you would know. Because if you know the secret S, you can compute AS. And by eliminating the AS part, you're left with the low rank matrix E. So you can check like in the end you get a low rank matrix E. So to find such secret brute force lead will take you around 2 to the k running time. Like let's say k just equals to n, then it's just extremely expensive. Or like if you know this low rank matrix, or we also call it low rank noise matrix E, you'd also know. Because if you know that E, you eliminate it, you're left with AS. And AS is just a linear combination of A. You can check that using Gaussian elimination. To brute force over all this low rank matrix, it will take you maybe around 2 to the NR. N is we call N is the dimensional matrix, R is the rank of E. So it's also extremely expensive. And what's amazing with this problem is that it's also extremely hard for all this heuristic algorithm that we have so far, despite many years of research. I'll show you a very complex table, but you don't need to look at too much detail. Just look at this complexity column. You can have some intuition that is extremely hard for like wide choice of parameter. And this is this just gave most major algorithm, like both quantum algorithm and classical algorithm on this MinRank problem. A little bit history, like this line work actually started from the seminal work done by Kipnis and Shamir for the interest of studying another, like the security of another crypto system. So people found out that if they can break MinRank problem, they can break that crypto system. And that is the reason that there's a long line work studying the hardness of this problem. And despite like around 2 decades or 3 decades of study, we still don't have like all this algorithm runs in very expensive time, like around sub-exponential running time. So in that regard, we have good understanding of the hardness of this problem. And because people believe this problem is extremely hard, people started to use it to build up some cryptography protocol, such as the signature protocol and the zonage protocol. And our focus today is to build up a public key encryption protocol from this MinRank problem. Yes.
So I thought the problem will be harder if k is larger, but according to the last attack, like it seems like when k is n square, about n square, it becomes
Do you mean this one?
The third one, if you count from the bottom.
1, 2, 3, this one.
Yeah.
So the minor attack plus this.
Yeah, it looks like if k is n square, this becomes very, very small.
Oh, wait. That's a good question. I think there's a typo here. It should be k plus n times n minus. Yeah, that's a good question.
If k is n squared, then s is n squared bits, then it becomes the same number of bits as
Uh,
the
it's
uniform distribution?
so there's a region like when the k is just around n square, but not exceeded by much. On that region, it's still hard. Like it's not ensured. Like yeah, it's still hard. So yeah, our question today is to build up public encryption from MinRank problem. Like we want to build up if we want to say like if a MinRank problem is hard, then we have a construction that our construction is a secure public encryption. So before our work, there were actually a few works that try to work on this, and what they achieved was that they succeed to build up a public encryption based on MinRank problem and some additional assumption. That's it to say, like they can only claim that the security holds if a MinRank problem is hard and their additional assumption holds.
You like LPM based PKE?
Yeah, it's like that. Like in LPM based PKE. In fact, the LPM is like a problem that's to say like it's hard for you to decode random linear code.
It's pretty similar.
It's very similar. The difference is that LPM works on okay, like this is a little bit like diving in deep, but if you know this, it's good that the LPM is working on Hamming-metric error correcting code. While the MinRank can be viewed as just the analog, but for Hamming-metric. That's why we also call this low rank noise.
But you probably like, I mean, you can get PKE from LPM with some extra assumptions, but I don't know if that's the latest. Like, you still need additional assumptions for LPM?
Yeah, that's a very good question. So actually for LPM, it's known that we can build up PKE solely from LPM. It's not known for MinRank. Yeah. Yeah, so we call this public encryption based on MinRank plus additional assumption structured MinRank. And what's the problem with this like structured MinRank? And it turns out like there might be some security concern vulnerability. So here I just show like this is a diagram from a survey paper, and the left columns are the constructions of such PKE based on structured MinRank, and the right columns are the attacks. And since the first construction of such PKE from a structured MinRank, there are already many rounds of attack, and then like another one try to fix and attack again and fix. And all these attacks were targeting on the additional assumption. So we still have good trust on this the hardness of MinRank. And our goal is to build up public encryption solely based on the hardness of a MinRank problem. And in this work, we just answer this question affirmatively. So we show that if MinRank problem as described is hard, then our construction is a secure PKE construction. Okay. So let's build up this PKE from MinRank together. Let's firstly try some strawman construction. So as a warm-up, so the public encryption is composed of three algorithms. Key generation algorithm that will generate the public key and the secret key. The encryption algorithm that takes the public key, that's what you have to send message to a friend, and the message. Decryption algorithm we'll see later. So let's try to control a strawman PKE. We will just use the MinRank instance A and AS plus E as a public key. And we'll use the secret for the MinRank instance S as a secret key. Now, in order to encrypt one bit of message, the plaintext M, which is either 1 or 0, the encryption algorithm that takes the public key will do the following. If the plaintext M equals 1, you will just output the MinRank instance A and AS plus E. On the other hand, if the plaintext equals 0, you will output the uniform random tensor of the same dimension. I can see like some audience already see like this is like I can see from your expression like you believe this is not secure, and indeed like this construction is an extremely insecure construction. The reason is that recall in the public key encryption setting, the adversary is also allowed to know the public key, which is A and AS plus E. So the adversary can just check whether the ciphertext equals to the public key or not. If it equals to public key, then that means it's encryption of 1. Otherwise, it's encryption of 0. So it's not secure at all. But what we can do is that we can, like in our paper as a bird's eye view, we can construct a very magic re-randomization algorithm. What the re-randomization algorithm does is that it will take the original MinRank instance and re-randomize it, output a new instance RS plus E prime. Both instances share the same secret S. And we can show that this re-randomized new instance R and RS plus E prime will look pseudo-random, even if you're given the original instance. Of course, like actually here, this re-randomization property will hold assuming MinRank problem is hard. So what we prove is that if MinRank problem is hard, then this re-randomization algorithm will re-randomize. And this will look indistinguishable from uniform random. So given this magic function, what we can do is that if the input plaintext equals 1, you re-randomize the public key and output the R and RS plus E prime. On the other hand, if the plaintext M equals 0, you just sample a uniform random tensor of the same dimension and output. Here I just arrange both in the same format. Yeah. And because we can show that this is a pseudo-random, so the adversary, even given the public key, cannot tell whether it's encryption 1 or encryption 0. The security just holds. Now, we also need to show that we can decrypt. We can, given the ciphertext and the public key, or we can, given the ciphertext and the secret key, you can decrypt and get to the original message. And to see that, recall that the secret key equals to the secret S. And if you're given a ciphertext which is either the R and the RS plus E prime, or R and RS plus a uniform random matrix, because you have both R and S, you can compute R or S yourself. It's just a linear combination of R defined by S. So you can eliminate the RS from the second part of the instance. And you're left with either E prime if it's an encryption of 1, or uniform random matrix if it's encryption of 0. And notably, you can distinguish these two. You can tell apart whether it's low rank or high rank. So if it's low rank now, that means it's an encryption of 1. Otherwise, encryption of 0. So you can do this if you have the secret key. So this is also a correct encryption scheme. But the question is, how do we do the randomization? Seems like a magic function that makes everything happen. And then now let's dive into a little bit. We see how do we do the randomization. What we do is we use a paradigm that somehow works magically for many of these post-quantum problems in the shape of A and AS plus E. It's also interesting that many of these post-quantum algorithms are in this shape, like A and AS plus E. And so this is a paradigm. We just try to use it. It turns out like it will not work if we just directly use it. We need our technical insight to make it work. But let me just show you what this paradigm is. So it's called Allegoric paradigm. What it does is that it samples a fresh noise, a low-rank noise E hat, and then it computes the inner product between E hat and each matrix of the original instance. And it turns out that we can show that if we do this, if we sample a fresh low-rank noise and compute the inner product between the low-rank noise and the original instance, the distribution will look pseudo-random, even given the original instance. Maybe I can give you some intuition why this happens. It comes from this idea of duality in many of these problems. So what does duality mean? It's actually not the, it's actually extremely simple. So it just says that if the original MinRank problem is hard, then if you do the following, if you start from uniform random tensor and sample low-rank noise and compute the inner product, this distribution will look pseudo-random.
Wait, what does it mean? With the inner product, you're computing. Can you go back a slide?
Yes.
What does the inner product mean exactly? Like,
Yes. So it means that, so that's a very good question.
Of like K plus 1 matrices. And they're like the same shape as like the E hat matrix. So it's the output of this inner product like the K plus 1 bits.
Yes, let's say if you are using the standard matrix product for Bennett inner product, then you get K plus 1 bit. Yeah, that's actually an extremely good question. This is actually why, this is actually the point where I will come back later. Just like, it turns out that if we use the standard for Bennett inner product, in the end, we cannot decrypt.
I don't know what am I supposed to know what the construction is right now?
Yes,
What is it?
the construction.
The re-randomization.
The construction randomization will be just use. Okay, let's say you just sample a low rank noise, random low rank noise, and then you compute the inner product between the low rank noise and each matrices in the original MinRank instance.
Yeah. Well, for example, that was like K or K plus 1 bits, right? But capital R from the previous slide was like NK bits.
Yeah, let's
like what's like a what's like what is capital R?
capital R. Yeah, it's actually a good question. So let me just looking ahead because you already asked. What we will do is that we will consider a general notion of inner product, where the output of inner product is not a scalar value, but a matrix. So it just satisfy the all these requirements of inner product, except that it's just like the output is not like a standard inner product. It will be a matrix. This is just looking ahead. Yeah, but right now I think you just asked a vital question. So to looking ahead, you can think it as like we just have some new notion in the product here. I'll introduce that later.
Okay.
Any question except the dimension?
Well,
And furthermore, like here, I'm just claiming that this will look random. Like,
Okay.
yeah.
Okay. I just want to see the motivation for you telling me that these two things look random if it's not. Well, since I don't know the relationship between this and the ultimate construction.
The relationship will be like this will be like ultimate construction will be the same, except we're not using the inner product that you mentioned. Because I never say that we will use that inner product.
Yeah.
Yeah. Yeah, so if you so in the paper we can show that if you if you do the randomization this way, this distribution will look pseudo-random. And thus like a security holds. Yeah, now I'll gradually go to the question that Ryan just asked. Firstly, I want to try to convince you that this inner product between E hat and the original instance can be rearranged in the shape of MinRank. At least it's composed of the two part by the linearity of inner product. So this part is what I mean R, and the second part is what I mean RS plus. Should I go back?
You can go in any direction you want. You want to go forward or not?
Question.
Yeah, sure.
But the entropy of R is way less than the original entropy of A.
Yeah, that's
low rank matrix.
that's a good question. So what we show is that if the MinRank problem is hard, then this will be pseudo-random. So the re-randomization will make it look still random for the diversity.
So is the R here 4 rank or that's lower rank?
Or here it's or here just this. I'm just saying that they can be arranged in the same shape. Yes.
I think R here is not necessarily a single matrix, right? It's like the both A layer is a sequence. So like you're taking a single like matrix, like E hat with a sequence of matrix.
Yes. So you're left with a
Sequence
like of inner products, like E hat with A1, E hat with A2, E hat with A3, up to E hat with AK. This is what I mean by E hat inner product between E hat and A. A is a tensor.
So it's R like uniformly and independently like sampled for each instance?
I'm claiming that this will look pseudo-random. So so right now I'm not I'm just claiming that this will be in the shape of a MinRank. At least syntactically, it will look like a MinRank. And during the decryption, recall that we use the secret S and we eliminate everything. We get one of these two cases. Either it's an inner product of a two low rank noise or uniform random, depends on the dimension. So in order to decrypt, we need to distinguish these two. That's what we saw in the bird's eye view. Yeah, I did abstract out some like details. I firstly just show you the bird's eye view, and then I tell you how do we do the re-randomization. I didn't define. I didn't say what the inner product we use. I just say that if we can arrange it in the shape of a MinRank, and now recall that in the bird's eye view, if you're given decryption, if you're given the secret, you can eliminate the R and RS, and you're left with either like one of these two terms. If we can distinguish these two, we can decrypt as what we did in the bird's eye view protocol. And now I'm gonna write Ryan's problem. Whether we can distinguish these two, or like what do I mean by inner product of two matrices? Yeah, so let's look through like the notion of inner product. So somehow like what we observe is that in the two-dimensional world, we can indeed distinguish the inner product of two sparse vectors from uniform random bit. By saying sparse vector, I mean that each vector only has few non-zero entries. And because these non-zero entries are unlikely to meet each other, so if you compute the inner product of two sparse vectors, it's likely to be 0. Now we're working on two-dimensional world. We're considering whether we can distinguish the inner product of a two low-rank matrix from uniform random. If we can do that, then we can decrypt. So let's see whether we can do this or how we do this. So somehow like the notion of inner product between two matrices is like less common compared to between vectors. So let me just give you some background first. The most standard notion of inner product for matrix is this Frobenius inner product. What it does is that it just treat each matrix it just take two matrices as input and output one value. You will just treat both matrices as vector. What it will does is that it will just unfold these two matrices into two very tall vectors by piling up their columns one after another, and then compute the inner product between these two vectors. This is the most standard notion of inner product, but it turns out that if we use this inner product in the construction we saw just now, you will not work. Because you will not work because somehow cannot distinguish the inner product between the Frobenius inner product between two low-rank matrices from a uniform random bit. Let me just show you, prove to you by picture. Like here are just two very low rank matrix, random matrix. Despite the low rank, but they still look not sparse, A. B still look somehow random, at least to your eyes. And if you just look any like some columns of each matrix, you look just very random, uniform random actually. So it turns out that the Frobenius inner product of a two low-rank matrix will be just uniform random. And if we use Frobenius inner product in the construction we just saw, in the end we're left with one of the two same options. We cannot decrypt.
But it also just doesn't type check, right? Like you're getting like bits in place of matrices in your R.
Yes. So yeah, that's Yes, it doesn't even pass type check as they said. Like, that's why like it may look very confused if you are familiar with forbearance in the product, because that's what the people see in most of this theoretic study. And that is actually one of the insights in our work, that we consider a general notion of so our goal is to distinguish these two to decrypt. I think I already covered that. So this is actually one of the insights in our work, that actually we can consider general notion in the product where the output of the inner product is a matrix instead of just a scalar value. And this is somehow reasonable in the sense, this is somehow reasonable for the MinRank problem, because somehow the low rank, when you say low rank or rank, it's about matrix. It's like a two-dimensional information. So in order to preserve this information, we consider this general notion of inner product where the output is the matrix. And in particular, we just invent a new notion of a matrix value in the product. We call it blockwise in the product. I will introduce to you how we define it. So syntactically, this blockwise in the product parameters by this parameter T will take two giant matrix, let's say E hat and E, and output a small matrix of dimension T squared, T by T. The T can be chosen from in range of 1 to n, and it's just a parameter. And this blockwise in the product will be computed in the following way. We will firstly divide the two giant input matrix into T squared many sub matrices. And then we define each entry of the output small matrix as the forbearance in the product of the two corresponding sub matrices. For example, here you can see the rightmost, the top right entry of the output is defined to be the forbearance in the product, what we just saw, of the two top rightmost submatrices. It looks a bit like a convolutional layer. Just, yeah. And turns out that we can show that this blockwise inner product has all the intrinsic properties that we want. Firstly, we can show that it can preserve the rank information in the sense that if both input matrices are very low rank matrix, then by setting T like correctly, the output matrix will stay to be low rank. So let's say if both E and E hat of rank R, then we can assure that the output matrix of the inner product has rank at most R squared. Oh. Yes, product. If T is larger than R squared, then you can do what we want. What we want is to distinguish the inner product of two low rank matrices from uniform random T by T matrices. Here, yeah.
Can you give some intuition for why this works?
Yeah, sure. It's actually very good question. So it turns out that we can show that the okay, we can firstly there's one fact that the rank of a tensor product of two matrices is equal to just the multiplication of their rank. So what that, and somehow what happens of this blockwise inner product is that it just output a sub matrices of the tensor product. Yes.
But in the setting of the paper, you will require T to divide the tension. But like as you mentioned, like this is kind of like a convolutional layer, so is it possible to have T doesn't like divide them, but like you do it like layer by layer, but also reduces the dimension and also like preserves the rank.
That's actually an extremely good question. So turns out we don't know. The reason that we don't know is because
Dependencies, like if you have any overlaps with this.
we don't know if not. I mean, if in this case we know how to show that the randomization will work. Like if we're using so I think to make sure everybody understands Ethan's question, what he asked was that whether it's necessary that we just divide these two giant matrices evenly, like T divide N. The answer is we don't know. The reason that we don't know is because if here like we do this, like we just divide the matrices evenly, we can show that if MinRank is hard, then the randomization will work. But on the other in the other case, we don't know whether we can show that.
What does evenly mean? Do you mean like the little squares do not overlap with each
All
other?
the doesn't overlap,
Okay.
and also doesn't overlap.
So basically you want the output to be like uniformly random.
We somehow want each entry of the output doesn't course with each other. Yeah, doesn't correlate with each other.
What would it change the size of, for example, last matrix to be a little bit smaller?
That's a very good question. So you can always do this interesting mental experiment. Like if T equals to 1, it's just the forbearance in the product we saw. And if T equals to N, it's a hidden product. And another way to show this rank bound is by knowing the fact that the rank of a hidden product equals to the product of the rank. Right. So this can maybe build up. This is actually a very good question. Yeah, so by setting the T, let's say a bit larger than R squared, we can distinguish the bulk in the product of two low rank noise from a uniform random matrix. And let's just recall in our precise view protocol, that's what they do during decryption. We just eliminate everything using secret key. We're left with one of these two. And now like we can distinguish the encryption for 1 from encryption of 0 if you have the secret key. So yes.
Can I ask? So
Sure.
like concretely, how do you set the parameters? Like what is T?
Yeah, that's a good question. Maybe I will because
Okay.
I think we actually have multiple choice of a parameter. We just provide a variance of parameter choice. They have their pros and cons. Maybe I'll cover it in the end because
Sounds good.
of time constraint.
Yeah.
Thanks
Yeah.
for. Yeah, and we can also show in our paper that if we're using this bulk in product in the re-randomization paradigm, where we just sample a fresh low rank noise and compute the bulk in the product between that low rank noise E hat and each matrix in the MinRank instance, we can show if MinRank is hard, then this will give us a pseudo-random distribution. So our security will hold. So in conclusion, this is our construction. Just use the MinRank instance as the public key, the secret of a MinRank instance acts as a secret key. To encrypt a message using the public key, if plaintext M equals 1, you sample fresh noise, low rank noise E hat and compute the inner product between E hat, bulk-wise inner product between E hat and the original instance A and S plus E. If plaintext equals 0, is the output uniform random tensor of the same dimension. And let's say the ciphertext is composed of 2 part A, C1 and C2. To decrypt using the secret key S, you can just check the rank of C2 minus C1s. Yeah, and now I will arrive Korn's question. So in our paper, just provide the variance choice of a parameter. These are for 1-bit encryption. The T is the parameter for the inner product, and the N is the dimension of the matrix. K is the number of slices. So for the first row, in general, the public key is of size n cube. N is the dimension of the matrix. And the first row it's the setting where you can make it very secure, extremely secure. But you need to pay the price of the ciphertext size. The ciphertext size is of size n squared, but it's secure against adversary whose running time is even 2 to the n to the 1/4. It's just like sub-exponential time. And the second setting is we have most of the same ciphertext of size like closely linear to the n. It's against any polynomial time adversary. So yeah, in conclusion, we just show that if the MinRank problem is hard, then our construction is secure public encryption. We achieve this by introducing this new notion of an inner product that preserves the rank metric. So for the future, so just now we saw that this efficiencies are just for 1 bit of message. It turns out like in crypto history, it really takes like a lot of work to optimize the efficiency of the encryption, balance the efficiency and security, starting from the first achievability paper. So I think first study is required to make the encryption more efficiency and towards practical. And on the other hand, and secondly, usually when we can manage to build up PKE, public encryption, from a hardness assumption, it's an indication that we can do something more, like more advanced cryptography. So here I just show you 3 lengths. The leftmost length is where we can only have some like basic encryption decryption. They are not public key. And we build up public key encryption from this assumption, somehow like take MinRank to the second line where we have public encryption. This is an indication that we can go furthermore and we can build up more advanced cryptography protocol from this assumption. So this is also an interesting direction for the future. Yeah, thank you. Now I'm happy to take any question. Yes.
So at the beginning, one of your motivations was blockchain.
Yes.
I was curious, where is public key encryption used in
Oh,
blockchain?
I think somehow in cryptography we just so I think signature schemes used in blockchain, and somehow if you can build the public key encryption, you can definitely have signature scheme. Yeah, and also it's this technique. Yeah, I think from complexity point of view, they oh no, they're not quite the same, but yeah, if you have PKU, you can build up signature scheme for it. Yeah. Yes.
You go to the slide with the parameter.
Yeah, sure.
You were just there.
Yeah.
Like for the first line, do you know how it compares with like a dilithium?
With
like, no, like the dilithium crystals thing in this.
Oh, I see.
Like I just know, okay, off the top of my head, like for factor, I guess that's that I guess 2 to the ciphertext size to the 1/3 or something. And you have like 2 to the ciphertext to the 1/8.
I think this is weaker because so here we're working on the problem of a matrix, but morally you can think everything in 1 dimension. You can afford the matrix as a vector. And what I'm saying is this. Maybe let me draw on the whiteboard. So I think I'm not, I don't know, exact capacity of the crystal, like exact best attack for the crystal system that I mentioned, but I can provide what I believe is a good way to compare these problems. Because there's like some difference of the description, like in this MinRank problem, we're considering a sequence of matrices, and let's say it's let me use small n, it's an n by n matrix. But in the problem of like a hemimetric, problem, like what you mentioned in those problems, usually the descriptions are a sequence of vectors, let's say of length capital N. And morally, we usually just take this and so usually the security parameter is proportional to this.
Okay.
And so I think to compare, I think it's more reasonable that you unfold this matrix as a vector and compile and make them align. Like here to describe this, you'll take your n squared bit. So I think it's more comparable if you think if you compare MinRank of size n squared to their capital N. Okay, so for people who are not familiar, I think the reason is that we usually, when consider security, we think that with respect to the input size of the algorithm. So what I'm saying is that somehow because each matrix takes n squared bit to describe. So in order to make the comparison of security fair, it's more fair to compare a MinRank parameter by n squared to those LPN of like where like the description are over vectors of capital N. Yeah, yes, sure.
So I guess it relates to the like concrete security parameter. So for let's say equivalent of 128 bits of security, like this n needs to be like 128 to the fourth power. What would be the like actual parameter you use in practice?
I cannot answer this question right now. Because I think usually when before you setting the concrete parameter, you need to have like a thoroughly crypto analysis study on those parameters. That is saying you need to implement these attacks and then work through them. Like, because sometimes when you're talking about concrete parameters, it could be a case where the log n cube is pretty large, or like, yeah, could be the case. Yeah.
So what happened to the third set of parameters that you mentioned?
Oh, I just want to save your eyes, just because here just show two options. One is more secure, but somehow has longer ciphertext.
Yeah.
The other way is like more succinct, but maybe security is weaker.
Yeah, and also can go like at the related works part, I think there's a concurrent work of this work, and you like your paper also solved one question raised by them. So like their PKE based on structured MinRank, but like your paper based on unstructured one.
Right, our paper is based on unstructured MinRank. Yes. Good question. Yes.
So, okay, so one thing that's nice about the LPN assumption is that it has uses in other domains like signal processing.
Oh,
So,
yeah.
like signal processing people spend a whole lot of time trying to figure out how to make it go faster.
Yeah, it's actually very
So
good
what
question.
equivalent for
I think, okay, actually there are different problems, actually, but somehow they look so similar to each other. And they can also be viewed as a problem like it's a hardness of decoding random linear code, but with respect to different metric, different noisy channel. And also for LPN, there are also construction like crypto protocol that are known only from LPN, like only LPN assumption can construct those protocol. So far, I don't know any such crypto notion that only comes from MinRank. So it's actually a very interesting directions.
Yes, to be a little bit more precise. So, does MinRank, if I came up with an algorithm to solve MinRank, would that help with anything else other than breaking crypto, or independently useful, or is it mostly cryptographers that care about it?
So firstly, it can provide you a very good decoding algorithm in coding theory, because this is MinRank is based on the hardness of decoding. And if you have a better tank on MinRank, it's actually not just a totally bad thing. Maybe it could be a bad thing for me, but it's not bad thing for everyone, because people, that also means like we have better decoding algorithm for rank metric code. Yeah. Good question. Yeah, sure.
Could you please tell me some basic idea about how to show the security, or specifically, to show that the inner product of E hat and A is pseudo-random?
Thank you for asking this question. I actually really want to show you this, but I'm out of time. Yeah. Yeah, so also it's good that we have already seen this we already see that MinRank is actually related to decoding. And somehow we can, for this decoding problem, we can have a dual version of this problem, in the sense that you don't need to look at slide right now, just look at me. So if the original problem is hard, then this dual, we can show that if the original problem is hard, then the dual version of the problem will be hard. And in particular, what is the dual version of MinRank? You just you firstly sample a random tensor, let's say, and then the second part is computed by you sample a low rank noise E, this yellow E, and then compute the inner product between E and each slices of the random tensor. It looks pretty similar like what we do, right? So if so what we can show that if the MinRank problem is hard, then this dual version of the problem will be hard. I'll prove to you by picture. Give me a few minutes. But why this would imply that the re-randomization would work? It's because here we say if H is uniform random, then given H, the second part will be pseudo-random. And in cryptography, we have this, we call it hybrid argument, is that if you replace this H with a pseudo-random distribution, this will still hold. And what you replace this with, you will replace this with the original MinRank. That's what happened during re-randomization. And let me show you why this MinRank problem with the, if MinRank is hard, that would imply that the dual version is hard by picture. So, so this is related to this coding theory, because you already asked, and this is after the presentation, I can go a bit deeper. So in coding theory, we have this notion of a dual code. So let's say A is the code, and the AS plus E is some new noisy code word. E is the noise. What is the dual code? It's also called parity checking. It's just the space, those vectors that equals to 0 when they are inner product with A. So it's those H that equals to 0 when inner product with A. Now I'm gonna show you by picture. So what really happened is that imagine you're given like some letters in different colors. And to give you intuition what the H really is, the H will just be those filtering paper, like transparent filtering paper that can filter out those red colors. Let's say the code is built up from the red colors. So it can filter out because by the property of H will the inner product between H and A will be equal to 0. So the filter paper here is this H when that if you're computing the inner product between H and the AS plus E, you'll filter out the part of A. And you're left with only the inner product between H and E. Now, why the MinRank will imply that this dual version is hard is because you can actually compute the random H from A efficiently. So if you're given A and AS plus E, you can compute H efficiently. And you can compute inner product between H and AS plus E, you somehow filter out the A. You're only left with some information related to H and E. And suppose you're claiming that the above is pseudo-random. Then must be the case that the below is also pseudo-random because you can get the bottom one from the above one. That right. Yeah, precisely. So that's how we show it. Yeah, but this if this is just way beyond what I was about discuss today. Yeah, I think that's all. Yeah, thank you.